able to like break down, sorry. For example, if you are able to break down the word into simpler form, then it helps to remove the disambiguity. Sorry, it helps to remove the ambiguity. That's why fine-grained POS tagging is very important. And also these coarse-grained POS tag are they are like fewer but larger component than fine-grained. And in a Nepali, any Nepali word, they are different from each other in these different features. So these are the features which represents the fine-grained POS tag. So let me give an example. Here, this fourth token is assigned the tag JM. So here it's a masculine adjective. This M is representing the masculine. So if we get rid of this masculine, which is gender feature, then we can map it to the coarse-grained, which is adjective. So now let me give a motivation for the using the fine-grained POS tagging for Nepali text. The very first reason is the Nepali language is morphologically rich. It's a complex language, and almost like 75% of its vocabulary is either a derived or inflectional word rather than head word. So the higher the number of the derived and inflectional word, then there's a high chance of ambiguous. So in order to remove that ambiguity, fine-grained POS tagging is really helpful. And Nepali word, it can be either inflected or uninflected. And as I mentioned, it's a rich in inflection system. And for example, I'll walk through briefly. First of all, like Nepali noun, they inflect in 7 different cases and in 2 dimensions in the numbers. And here is shown in the table, all of these in the boxes, they are all post position, which appears at the end of the word. And this post position mark the noun inflections. Similar is the case for the pronoun inflections. It also inflects for 7 different cases and 2 dimensions in the numbers. Similar to noun, these pronouns are also marked, from inflections are also marked by these post positions. And this beginning are the pronoun and the word at the end, these are the post positions. And for adjective, Nepali adjective, they also inflect in 2 dimensions in gender and numbers. Here, for masculine, it ends with the word with the character O, and for feminine, it ends with the character I. And for plural cases, for both of these gender, they end with the character A. The last one, the verb inflection. Nepali verb inflects for these features: tense, aspect, mood, person, number, and honorificity. Any particular Nepali verb, it can show more than like 20 inflection forms, and which are not limited to the ones shown in the table. And since I mentioned earlier that Nepali is rich in inflection system, especially in the verb, because as we can see here, there are a lot of features for verb. And because I'm focusing on only in the inflection, because the majority of the Nepali word is formed because of the inflections. Now, let me be a little bit more detailed about why fine-grained POS tagging. So as I mentioned earlier, these particular words are encoded with the grammatical features, and it helps to, by using the fine-grained POS tagging, it helps to remove the ambiguity. And if you're able to remove that, then it provides a better accuracy in NLP applications. Let me give an example here. So here are 2 sentences. I'm focusing on the word, this highlighted word. This is a verb in the Nepali, its corresponding is in the English is lived. Both of these words have the same root word here, but they are the inflected forms. So this is due to the verb inflection. And the both word in the sentence 1, this verb is representing that, okay, the subject is doing the work. And in the second sentence, it is representing that subject is making someone else to do the work. So in that case, it is representing the different meaning in different context. So this kind of ambiguity can be reduced if we are able to perform the fine-grained POS tagging. Also, there are some limited works on fine-grained POS tagging. Most of the prior work in Nepali, like most of them are coarse-grained, except the one here at the very bottom, which is the performed on fine-grained on 112 tags. It makes the use of lexical analyzer with some disambiguation module. Okay. So this is the fine-grained to coarse-grained POS tagging mapping, because we want to see how well this fine-grained is performing. So we want to do some kind of mapping first. And in our work, we use a 112 POS tag inspired from this work by Hardy and the group here. And we map this fine-grained tag to the coarse-grained, which is taken from the ball and the BK, which was also inspired from the Pentry Bank. And here we reduce few of the tag because some of them were null and some of them were like header list, which were not important. So we reduced to 39. And one thing to notice here is, yeah, moving from from coarse grain to fine grain, there's a sparsity in the tag. Some of them is a one-to-one mapping, and some of them are like many-to-one mapping from fine grain to coarse grain. So moving on to the model, we implemented the pretty standard sequence model, BiListem, BiGRU, and BiListem CRF. In this figure, we can just replace this BiListem with BiGRU. They are both are like a variant of the RNN. First of all, we're given these tokens, and these tokens are like faded to the embedding layer. In our case, we tried two kinds of embedding. One is bare embedding, where the weights of these tokens are initialized randomly, and it's trained during the training process later. And the next one is we tried with the multilingual BERT embedding also, because we want to see how well it performs using this multilingual BERT embedding. And for bare embedding, we use a dimension of 300, and for multilingual, it's a pretty standard one, 784. Once we encode in the vector representation, we fetch it to the BiListem layer here. These forward and backward the forward and backward LSTM, they are used to capture the hidden information, and it provides the probability of particular for the tags. Here, the softmax distribution is obtained for each of these tag, for each of this token. And then finally, it is fetched to the argmax, where the token with the highest probability is picked. And we also implemented the BiListem CRF here. The only difference is the output from the BiListem, which is fed to the CRF here. We added the CRF in a sense because some of the tag like VVY and YN1, it can never be followed by another tag IA in Nepali. So this kind of like tag syntax has to be captured. So in order to, and this kind of tag syntax can be captured by using CRF. So that's why we added the CRF on the top of the BiListem layer. So for the evaluation, we use the Nepali National Corpus. This corpus contains like 17 million manually and semi-manually tagged word. And here's the distribution of the corpus. Even though like we mentioned the 112 tags, only the 109 tags were present in the overall data set. 3 of them were not present. So we did evaluation only on these 109 tags. And these detail of these papers is on detail of this corpus is in this paper here, construction and annotation of corpus contemporary Nepali. And here is the top 7 and bottom 7 distribution of this tag for both fine-grained and coarse-grained. Now I'll move on to the quantitative finding. So we want to see whether this fine-grained is good enough to apply or not, because moving from coarse-grained to fine-grained, the tag gets sparse, and we want to see whether whenever the tag gets sparse, it's performing well or not. So for the very first step, we want to see how well these fine-grained and coarse-grained perform across all these sequence model. And from this table, we can see that BiListem CRF with the bare embedding performs best across all these model. And here, looking at the performance for like bare embedding for BiListem CRF, BiListem, and BiGRU, they're pretty similar, but it is doing slightly better. And this is achieved by adding the cost of adding the CRF on the top of BiListem. Also, BiListem CRF with the bare embedding does perform the best. And we also compare the performance for bare and BERT embedding, and this multilingual BERT embedding, sorry. And what we found is that the bare embedding was doing better than its counterpart, multilingual BERT embedding. And it was doing better by approximately like 7 to 8% in both fine-grained and coarse-grained. So now we know that this BiListem and BiGRU, they are also doing pretty similar here. And then overall, throughout this sequence model, they are doing similar. And the best one is BiListem CRF. Now, we want to see how will these fine-grained POS tagging perform compared to coarse-grained. And our best model here, the BiListem CRF, is doing better by 0.03%. And I wouldn't say this is not a significant improvement. So that's why I would say they're doing pretty good. These fine-grained and coarse-grained are doing as good as each other. So now we know that fine-grained POS tagging does better. It does as good as the coarse-grained. Now we want to see how will these fine-grained perform within each tag. So we want to see whether this fine-grained is performing better only because of the tag with the highest distribution, or it is doing better in the other tags also, because in the fine-grained, it has like more number of tags, it is sparse, right? So from this table, the one here highlighted, it shows that like this 90% of this tag are above like 90% F1 score. 8 of them were between 80 to 90, and the remaining 10, out of which 6 of them were underperforming here. And we also observed that the tag with the highest distribution, this is a common noun, it was slightly underperforming compared to the another tag, which was second highest, this post position. So now we can see that, okay, this performance is not precisely correlated with the tag distribution. And also we observed across other tag, because we want to see whether it's performing across throughout the tag or not, right? So we also observed that except for this 4 tag at the bottom right, the other several tags with the low distribution were also tagged correctly. So they were doing pretty good. So then we know that, okay, fine-grained is doing better, it's good enough. And now we know that even though it's sparse, it's doing better for most of the tag. Now we want to see how will these fine-grained perform corresponding to its coarse-grained tag. And as I mentioned earlier, there are 2 types of mapping. The one is many-to-one mapping, and another is one-to-one mapping. So first of all, let me go through the many-to-one mapping. In the many-to-one mapping cases, like most of these fine-grained tags were within the 2% of the performance. For example, here, the tag DTM, which is a coarse-grained tag, is corresponding fine-grained 9 out of 12 tags were within the 2% of this coarse-grained tag. And except the one with DJM and DJO, which were underperforming. And there was a tag DJF, which was not in the test set, so we discarded this one. Similarly is the case for the tag PP, for which is corresponding fine-grained tag. 5 out of 6 were doing similar performance within the 2% range. So now we know that, okay, so fine-grained, moving from coarse-grained to fine-grained, even though it's sparse, it is doing better. So at least like 50% of these tags are doing good. So similarly is the case for the one-to-one mapping. For most of these one-to-one mapping, they have the similar performance, except for the one tag with the tag QQ, where the performance for the fine-grained tag POS tagging was better compared to the coarse-grained POS tagging. And on looking the precision and recall, both of them had the same recall rate on the fine-grained and coarse-grained POS tagging, but the precision was higher in the fine-grained, so it was performing slightly better. Finally, the key takeaway. So our main goal was to see whether this fine-grained POS tagging can be applied in the Nepali text or not. And with the large enough corpus, we found that, okay, fine-grained POS tagging can be, it does perform as good as the coarse-grained POS tagging in Nepali text. Also, we tried with the 3-sequence model, the deep learning-based model, and it outperforms the state-of-the-art Nepali unitag tagger. This prior work makes the use of the lexical analyzer and some disambiguation module. So it has a disadvantage in a sense because this has to make use of some rules.
I think you have to wrap up.
Oh, sure. Yeah. Sure, Professor. Yeah, this is the last slide. Yeah. Sorry. So as I mentioned earlier, this multilingual bird embedding was not performing better compared to bare embedding. And we have left this as a future work where we can explore the multilingual bird vocabulary, which will give more intuition into why the multilingual bird embedding was not performing well. And okay, thank you for listening. And I want to thank my collaborator, Shrestha and Dhakal. And you can find our other works in Nepali in this link. Thank you. I think I can take the question now.
Thank you very much. One question, please. Okay. Is there any question? Okay, thank you very much. Let us continue to the second one. Thank you very much, Doctor. The second one is a morphological annotated corpus and a morphological analyzer for Egyptian Arabic by Amany, Fashwana, and Professor Sameh Alansary. Is Amany here? Start from the beginning and share, please, slideshow. Go ahead. Amany? Amany.
Sorry. Unmute, sorry. Okay.
Okay.
First of all, I would like to welcome all the attendees and the conference organizers. Now I'm going to present our paper, which is entitled A Morphologically Annotated Corpus and a Morphological Analyzer for Egyptian Arabic. It's an in-progress work for building a morphological analyzer for Egyptian Arabic, where we can see now that Arabic dialects in the past, generally not linguistically well described, but the last few years have witnessed a noticeable increase of Arabic dialect textual data. After the emergence of social media network, the data become everywhere, which motivates the work on developing NLP applications for these dialects. Nevertheless, the NLP of Arabic dialects is still in its early stages. So when we start to discuss about this work, we start to build a morphological analyzer, since it is an essential step in most NLP applications, such as machine translation, information retrieval, text summarization, text categorization, and so forth. When we check the related work, we find that there are two directions for modeling dialectal Arabic morphology. The first one depending on extending the MSA tools for covering dialectal phenomena on the top of Backwalter Arabic morphological analyzer, such as the indicated related works. The second direction interested in modeling dialectal Arabic morphology directly. And there are some trials for building corpora that interested in building multi-dialect, multi-genre morphological annotated corpora that include e.g. Such as the showed works and other dialects, which are related to our works where they follow some approaches, similar approaches to our approach, our followed approach. Another related work to our work is the problem of how they handle the lacking of standard orthography, where we find that a few trials, they try to handle the problem of lacking standard orthography, and the most used one of this is which proposed by Habash et al, who provides details description of convention of orthography for dialectal Arabic coda, or what's called coda, where a unified common set of guidelines and metadata guidelines are applied, is presented to help in creating dialectic specific conventions, and it covers 20 Arab cities dialects, including Cairo, Alexandria, and Aswan, for example. But after reviewing the related work to our related resources and tools that are used for building a morphological analyzer for EG, it can be noticed some that none of the reviewed corpora present a well-linguistic description of Egyptian Arabic morphology or clarifies if there is a formalized morphology for EG or not. They don't represent enough variety of resources and and their POS tag set are not suitable for the EG. Their conventional orthography is not linguistically driven. Therefore, it is preferred to build an annotated corpus that provide conventional orthography guidelines and develops a more suitable POS tag set for the EG. So when we come to the corpus compilation and the pre-processing of our corpus, we can find that the data is collected from different sources such as social media box and other web articles written in EG, and it covers various genres. It has about 500,000 words written in Arabic character where no translated words are included, and some decision related to what the proportion between different sources, subsources, and genres in the corpus are taken up in the length or nature of the text and how common the genre or the source in Egypt. As we know, we can find that, for example, Facebook is the most source of social media is used in Egypt. Only 5 types of social media sources are included in the corpus design as subsources. Each file is pre-processed, and the metadata about each file is kept with their information about file name, publishing date, and so forth. And this is the this table shows the cover subsources of social media and the covered genres in our compiled data. And when we come to the corpus annotation, there are some resources we used where the concatenative approach, lexicon-driven approach, is proposed for developing our morphological analyzer. It resembles the adopted approach in Backwalter Arabic Morphological Analyzer, where the proclitic in our approach, we use the proclitic word form enclitic representation, while in BAMA, a simple prefix stem representation is proposed. And this system depends that morphotactics and orthographic rules are built directly into the lexicon itself, instead of being specified in terms of general rules that interact to realize the output. It contains the 3 components: the lexicon, the compatibility tables, and the analysis engine. For example, the word يقولوها is represented as this show how this word will be represented in our system and in BAMA, and show the difference between the lexicon, the proclitic word form enclitic, and the prefix stem suffix representation. Since MSA and the colloquials do share a large proportion of their lexicon, consequently, it is preferred to get BAMA's analysis solution for those words that are common between MSA and EG. Some modifications are needed to be compatible with our proclitic word form enclitic representation. And out of the unique words in our data of 82,000 words, there are about 41,000 words are analyzed by BAMA. But while assigning the part of speech to our system, in our annotation process, the tags are considered as much as possible to be near to MSA Arabic MSA tags. Nevertheless, not all tags that BAMA provides are suitable for the linguistic characteristic in Egypt. Some we can find that some tags are added and others are modified to be compatible with the linguistic nature of EG. And these are some examples of added proclitics, enclitics, and main tag of word form. And this at the current state, we have about 35 tags that are used in the word form, the main word form, and these are some examples of these tags. In our corpus comparison, there are a lot of orthographic variations as known in EG and all Arabic dialects, and there are inconsistency in writing the dialectal Arabic text. So the most as mentioned above, the mostly used convention is the coda. Nevertheless, it is prepared to follow our guidelines to handle this problem of lacking or conventional orthography. Since coda is complicated, as it has long lookup table for those EG words that don't have MSA cognates. In addition, coda decision prioritize the MSA spelling, which is unnatural when it comes to how people write or speak, and not suitable for some applications such as text-to-speech or speech-to-text conversion. The decision is taken to assign conventional orthography for each word to be close to the EG pronunciation as much as possible, regardless the way a word is typically written, where each word is associated with conventional lemma and the word form alongside with its original word form, where no editing to word form is done, except in some cases where if some letters are missed, added or transposed, in the case of words that have speech effects, or in the case of shortened long vowels. We can say that we treated with Hamza and final Ya or Ta marbuta to follow the same rules of those of MSA, except in the dialectal form of Ta marbuta, which is not found in MSA, which is the middle non-construct as in word Arfani, she Nomi. Is preferred to be, it is transferred to be عارفة تاء مربوطة to plus ni. Some phonological assimilations in MSA may be written to reflect the phonology or underlying morphology, such as the word جنب in MSA Arabic, also written in EG as جنب, and in this case جنب is selected as a conventional word form. Some clitics have multiple common forms, for example ha, that appears as a separate word or as a proclitic. In both cases, it is annotated in proclitic as a future particle. The negation ma may be written as magash, two words, or as the proclitic magash or magash. Only ma is considered as a proclitic, and in the case of magash that contain mim alif, the word must be split into words. The different spelling may add some confusion in AG writings, such as, for example, the word shafu may be shafu, they saw, or shafu, he saw it. The decision is taken to edit the enclitic of shafu to be ha, since wa stands for the plural form. The problem of indirect object pronouns that may be attached to words and add some confusion. For example, أقوله, that may be segmented as أقوله, أقوله, I said it, or must be split and on into two words, أقول له, I said it to him, and we separate it in this case. The last case. There are some phonological differences between MSA and EG. We need to discuss here, although the focus on morphology, and what we need to discuss it's here. So we decided a lot of decision depending on this phonological features, such as tha, which is not found, tha and that, which not found in EG or not pronounced in EG, but replaced by ta or sa or da or da are respectively as followed in the figure, and the consonant the, which may be which may pronounce it as da or za, and in addition the consonant qa is usually replaced by glottal stop in most regions of Egypt as in word adim, but in Upper Egypt it's pronounced as gadim. And the decision was taken to depend on the only in this case of qa on the MSA form to unify, like but in other cases we selected the ta as tom, تعبان, and in some cases of words that's related to a specific culture as ثورة, we depend the word ثورة to be used in our conventional orthography. For quality control and the inter-annotation agreement, 5 files of total 3,153 words were tagged independently, and we show that 195 words show some disagreements. All these 3 agreed on about 88% of the words, and the pairwise agreement is at least 93.7%. And we, for ease of annotation process, we use this built application. As you can see, each word is separated by clicking on the word. The annotation is appeared, and the annotators can find other contexts to analyze at once, or edit or search about solution if he edit the word or separate the word and so forth. And this is an example of our annotation after the ending annotation process. In the current stage, about 527,000 words, representing about, as mentioned above, 82,000 unique words are collected, and about 239,000 words are morphologically annotated by well-trained linguistic annotators. Each word is associated with information about, e.g., conventional lemma, MSA lemma, procletics, original word form, and the conventional word form, incletics, glossary, number, gender, and definiteness. The lack of standard orthography is handled by setting the conventional word form lemma that is close to each pronunciation, and the annotated words along with the future annotations will be used for building lexicon and compatibility tables, which already now built after publishing our paper. And we can see now that we have 3 lexicons of procletics and word forms and incletics. These 3 lexicons are the main 3 lexicon used, and there are 3 compatibility tables that check what is available to be compatible from procletic with word form, and the second compatibility table check what is available to be compatible with between a word form and incletics, and the third one is showing the compatibility between procletic and incletic. The 3 compatibility tables must be get through at once to detect that it is a valid solution. And this is an example of output in the current stage, which indicate word form, convention, orthography, and so forth. And it's all about work in the current stage, and thank you.
Thank you very much. We can take questions. So any question? Any question? I will ask you one question. We have, for example, the word احتكار, monopoly, احتكار بالكاف. And in Egyptian, it is احتقار بالقاف, like humiliating. So how do you handle something like that?
As I said, the nearest to the pronunciation.
No, with the pronunciation, احتقار is احتقار. In Egyptian Arabic, احتقار means humiliate, and احتقار, if we take it as it was in modern standard Arabic احتقار, it will be the same pronunciation.
I think in this case, we will the gloss will differentiate between these 2 words. If I take the word احتكار as احتقار, I think in Egypt they pronounce it as احتكار.
يعني
I think so. I think in Egypt they احتقار, we know احتقار is يعني to عشان احتقر الشخص يعني.
انت مش فيرب، لو استخدمتيها كنون احتقار.
But I think they are different in Egypt.
يعني if you have any case that the word
in the case according to context the word is written as احتقار, but the writer mean احتكار, in this case I will edit it.
Okay, thank you.
Okay.
Thank you much. We have the third paper, which is AraScore, investigating response-based Arabic short answer scoring. Abdelrahman, ElNaka, Omar, Nael, and Hadeel, Afifi, and Nada, Sharaf. This is 1, 2, 3, 4. Let me see. Okay, I think. Okay, this paper is he is not able to present it, so I am going to share. Okay. I'm sorry. This is not the paper.
Hello everyone and good evening. Today we'll be presenting our paper AraScore, investigating response-based Arabic short answer scoring. This research was conducted by Abdelrahman, ElNaka, Omar, Nael, Hadeel, Mustafa, and Dr. Nada Sharaf. First, I'll be giving an introduction about our paper and the motivation behind it, along with a brief background on some related work. We'll also discuss the implementation details and the respective results. Finally, we will conclude by discussing some limitations and future work. Okay. Currently, there are more than 80 million students in the Arab region. On the other hand, there are roughly 2 million teaching professionals with millions of gradable papers and exams. This takes huge amounts of time to thoroughly evaluate and grade. So this raises our research problem. Can we create an automated system that would aid in grading Arabic short answers so that teachers and other professionals can direct their efforts towards other educational aspects that will surely increase the quality of education in the region? Yeah, automated scoring is really not a new concept. It has been around for a long time, and it's heavily utilized in MCQs, for example. But this is a relatively easy task, and usually MCQs are not the most preferred method of assessment, as it really doesn't provide a proper evaluation for the student. Unfortunately, the rapid growth of NLP has allowed the development and the research of automated short answer scoring and essay scoring as well. So scoring systems are split into two segments: reference-based and response-based systems. Reference-based systems make the use of a reference answer that is compared with each student answer, and the score is assigned according to a similarity measure. Usually it will be the cosine similarity. On the other hand, response-based systems do not use a reference or a model answer. They'll use machine learning and statistical methods to train a model on a large number of answers. This model can later be used to predict the score of future answers. Unfortunately, only minimal research has been conducted to develop an Arabic scoring system. Maybe only 1 or 2 systems. You can find the references here. Well, reference-based systems are an efficient method and they're easy to implement. They're only accurate when scoring answers that achieve the full grade, because we're comparing with the model answer. There are many nuances and complex features that really cannot be captured by the cosine similarity only. So this is why we chose to explore machine learning models to implement our system, where the patterns of each class label are detected at glint to give accurate predictions for future answers. In this project, we use 3 different data sets. First, we manually translate 1,500 answers from the Kaggle short answer scoring competition dataset. The second dataset is the Arabic automated short answer grading dataset. Consists of 2,000 answers approximately across 50 questions, I think. And finally, our new open source dataset, the AraScore dataset. We collected a grade 7 social studies graded exam from an Egyptian private school. The exam consists of 5 questions with 30 answers each. The topics are mostly geography and history. Due to the small size of the dataset, we performed extensive data augmentation using a technique called back translation. We increased the dataset size from 150 to roughly 2,500. I'll explain in detail what is back translation. So what is back translation? It is simply translating a sentence to a target language, then translating it back to the original language. And due to the inconsistencies in training translation data of neural machine translation models, most of the time back translation will output a paraphrase of the original sentence, which can be used as an augmentation technique. In this project, we used a variation of back translation called chain back translation. It's basically the original sentence is passed through multiple stages, then back to the original language. So this most of the time will produce a better paraphrase than single back translation. You can find this, it's clearly demonstrated in this example. You can try it yourself using Google Translate. In this section, I'll discuss the preprocessing steps and experimental setup. We basically perform the same steps for each of the datasets. First, we lematize all of the answers, and we also count the length of each answer as we use it as a feature in our models. Then we vectorize our answers using 2 methods. First, we use AraVec. So we produce a word embedding for each word in the sentence, and we average all of these embeddings to produce one fixed embedding that is a representative of the sentence. So it's basically generating a sentence embedding using by calculating the average of all word embeddings in the sentence. We also use the AraSif to generate the sentence embeddings directly. Later on, we will compare both techniques and the results. And since the dataset sizes are small, so we use the cross-validation, leave one out cross-validation. So we approach the task using 2 methods. We approach it as a classification task and as a regression task with the score approximation. We used 3 different models to implement our system. We used the random forest and a support vector machine, and finally a multi-layer perceptron. Regarding the random forest and the SVM, we performed a grid search to find the optimal set of parameters. You can find more details about the exact parameters in our paper. And regarding the multi-layer perceptron, we manually tuned the hyperparameters. Regarding the architecture of it, it consists of 2 hidden layers having a ReLU activation function. And the output layer, we use a softmax activation function with a categorical cross-entropy loss, since it's a multi-class classification for classes. We also used an Adam optimizer. The only difference in the regression model, in the multi-layer perceptron regression model, we did not apply an activation function in the output layer. Okay, so in this section I'll discuss the results for both the regression and the classifiers. We can see that using sentence embeddings along with the multi-layer perceptron, this produces the best results. Maybe the difference isn't really huge, but I think it's still a good performance gain. These are the results for the classifier models. The same thing applies. Using sentence embeddings with a multi-preceptor and classifier still produces the best results. And as I said, it's really not a huge difference, but still I think it's a good performance gain. So to wrap up our presentation, we successfully built an automated system that can score short Arabic answers. We also found that the sentence embedding approach was better than the averaging technique using Arabic, most probably due to the loss of information when averaging all of the word embeddings in the sentence. We also found that neural networks are a better candidate for this task. The multi-perceptron performed better than the SVM and the random forest, also most probably due to better feature extraction. And finally, we publicly released our dataset, the AraScore short answer scoring dataset, so others can further explore it and validate it and perform any kind of research on it. These are some suggestions for future work regarding this project. I think more neural network models should be investigated, such as RNNs, LSTMs, and using potential mechanisms. Maybe even BERT or something, or transformer-based language models can also be used for this task. I think it will produce great results. I think this project will also benefit from collecting a real large-scale dataset and performing augmentation on it. That's it. I hope you like the presentation. For any questions or feedback, please send us an email at any of the following contacts. Thank you for listening. Hope you liked our presentation. Have a good day.
Excuse me, sir. You are not audible, sir.
Okay. Actually, the best. That's why I said that the best I can do is that present the recording, because the authors are not available and they send us this, so we give them the benefits of the doubt.
Hello.
Yes.
So we actually managed to attend. So Omar and I are here. In case
Actually,
anyone has questions, would be gladly to answer.
You hear the noisy. This is actually I can tell. So any questions for the paper, because Nada is already here? Any question for Ara, what is the name? AraScore, investigating response-based Arabic short answer scoring. Maybe they couldn't follow because of the noisy. For myself, I couldn't. But do you have any questions? Any questions? But Nada is here. So Nada, since you are here, I will give you the chance to just give a brief about your paper very quickly in terms of contribution.
Yeah, actually, Omar is here, so he will
Yes, I can
go
answer
ahead.
the questions.
So Omar, what is the challenges and what is the contribution that you have made in 3 minutes?
Okay, the challenges we wanted to implement a system that can automate short answer scoring in Arabic using machine learning models. So we did a comparison with 3 different models: the random forest and the SVM and the multi-perceptron. We also collected a data set and performed some data augmentation techniques on it. The back translation I explained in the presentation. And that's it. We performed the comparison on 3 different data sets, our data set, and 2 publicly available data sets. And we publish the results, and we also publish the data set.
Excellent. Thank you, Omar. Thank you, Nada.
Thank you.
Any questions?
Thank you.
Any questions to Omar and Dr. Nada? Let us switch to the fourth paper, which is Assamese word sense ambiguation using Cuckoo search algorithm. And I think we have a video. So I'm going to share the video, and also the author said that they are available. And
Sir, excuse me, sir.
yes.
Sir, our group member Arjun Gogoi is available here for present.
Okay. Please, go ahead and present.
Okay. Sir, he is actually can't able to unmute his mic, sir. Oh.
Say it again.
Sir, he is not able to unmute his mic, sir.
Okay, let me go. What is his name?
Arjun Gogoi, sir. ARJUN space
Okay.
GOGOI.
Okay. Arjun, I am trying to ask him for.
Yes, sir. Yes, sir.
Okay.
It has worked, sir.
It
So actually, due to technical issues, it may occur. Thank you, sir. So let me.
Most welcome.
So yes, sir. It had worked.
Most welcome.
Sir, is my screen visible?
Arjun started. Yes, it's coming. Yeah, okay.
Yes, sir.
It's not yet.
Not honorable members present out here. I hope you all are well and good, staying safe in these tough times.
Aaron, please.
So my name is Ongu, and I'm currently pursuing Bachelor of Technology in Computer Science in
Aaron.
Now I'm going to entitled as Words and Disambiguation. Dr.
Arjun, you are not actually audible clearly. Arjun, please hold on.
Motivation.
Arjun, please hold on. You are not clearly audible actually because of some network issues, I think, at your side. Arjun, please.
He's not listening. Arjun.
References. So what is Watson's disambiguation? Watson's disambiguation problem of determining which sense is occurring in a person or
Arjun, can you please listen us or other members from the same paper?
Might be no sentence, but as a human we can identify
Only
ambiguous word mean to a particular context, but we will know. Objectively, some
Sir,
ambiguous
Lakya
words
excuse me,
Jyotina,
sir.
and to find its actual meaning
Yes,
using
sir.
various
I think he has a
methodologies.
serious issue with
Let's
his
take an
laptop.
example.
So
So,
I
for
think
please
you
example,
ask
should
him to
share the
please
screen.
ask him to
Bono
stop
Hodai and
there.
Mr. Loikho Ibo Lage.
Yes,
The
sir.
English translation is everybody must
Actually,
have
I
ambiguous.
am.
Second example is Kho Mur Bha Bondhu. The English translation is Kho is my good friend. The for example notes an aim.
Aaron, you are not listening to us. There's a lot of noisy from your side. Also, you are sharing the window tab, not the presentation. So share the slideshow, please. We have difficulties listening to you or following you.
Excuse me, sir. Sorry for the inconvenience. Sir, I think you should share the video instead of share him because
I
I
don't
think he
have
has a
his I
serious.
don't have his video. I don't
Okay,
have
sir.
his video. So those who are not able for some reason, they send the video. And some of them they said, just in case this is my video. That's it. Aaron, would you like to send? Do you have a video? Maybe you didn't record. Aaron,
Lakya Jyoti, I think, is the another author for the same paper. Lakya, if you are good at the network, so if you can, I think, present on his behalf. I think if you have the presentation and can present, I think you are getting a good network at your side.
Yes, sir. I'll try, sir.
we can go to the last one until you sort this out with your colleague.
Sure, sir. Sure, sir.
Okay.
Loikho, hello.
Yes. So the last one I think is available.
Yes, me is here.
So could you please share your presentation, start presenting?
Sure.
So now we are going to, unfortunately, I don't like to do this, but so we're going to have the 3D CNN-based dynamic gesture recognition for Indian Sign Language modeling by Dushyant Kumar Singh.
Good evening, all. Hope I'm clearly audible to everyone present here. And even my PPT is clearly visible to you. Is that so? May I get the confirmation?
Yes, this is not the slideshow. It is the PowerPoint. This is the PowerPoint slide.
I'm doing that. I'm doing that. Don't worry.
Okay, but we are seeing this.
Sure. So
go to slideshow in the red line.
Sure. Just hold on. So what we have is
yes.
Yes. So this is what means is the thing, the work which we had actually done and going to discuss here, rather means present here to have views on it, and certainly how it actually means will affect the things which are there in the market or in the ministry, or you can say the literatures available, how it can be compared with that. So me as Dr. Dushyant Singh from Allahabad and IT Allahabad, India, and the work is regarding dynamic gesture recognition towards Indian Sign Language modeling. So it's a pretty different. I mean, it's just a slight difference this work is having when we look the parallel papers being submitted or the manuscripts which are here in this conference, rather in this session too. So this conference all moves around NLP, natural language processing, and certainly here again a kind of language processing and the language modeling is exercised, but the inputs, kind of inputs being taken means for processing is not text actually, is some video or the major information. So these are the video clips of the gestures which are being the inputs to this work, and certainly those are then processed for some gesture based sign languages. So this is how we will go for. So introduction, survey, the proposed approach, the gesture data set. Actually this has been created by our own self. No way that the things are available in the literature, means they are the repositories they where something is available, but many things needed to be created or synthesized from our own self to improve the things, improve the approaches. So certainly some data set has been created, and experimentation and the conclusion. So actually talking about hand gestures, uh, so means if we talk about the vision application, so gestures are the largely used traits actually, and means hand gestures are alternative in many circumstances to the spoken communication. So when we have the verbal communication, so not only the language which we are speaking, so these gestures actually come into play and actually plays a good role many a times. So if we say the communication, so the component of these gestures many a times in many of the languages it is not less, and typically it is 30 to 40% component which actually defines the language and complete. Gesture recognition then comes to be a good problem nowadays to talk upon. Uh, so this is what means is being proposed here, and let's see how we can recognize gestures from the video snippets or the video streams or the video footages, or in real time video streams we can say. So means so how it can be done. So certainly a typical image processing is required for it, and the newer concepts and advanced image processing techniques had actually made it more possible and boosted this kind of the task. So finally, means the objective is to model the sign languages, signs actually, means Indian language, sign language symbols, uh, means created through hand gestures, and we need to interpret them for some meaningful information. So how it can be done exactly? So this has been shown here. So and it's now is the time where means it's of vital importance. It's getting its importance everywhere. Means let it be in playing games like PS4 or PlayStation, or home automation, gesture controlled lights, and gesture control means everything means around us. Okay. So now it's playing a big role in virtual reality, you can say, or so that is what the importance of this is. So how can that be done? How this gesture recognition can be done? Hand gesture recognition. Typically talking of, so there could be different kind of gestures, not only hand. There are many different kind of the gestures from lips and various face movement and all. We will just be talking about the hand gestures only. So how can these be modeled actually? So typically there are two main approaches. So one is physical sensor based. So we know that hand gestures are modeled through those gloves are there, means accompanying those sensors, typical physical sensors, you can say. And as soon we move those sensors, the kind of sensors are accelerometer, gyrometer, and gyroscope, and like that. So, and they have more than that too. So as when we move our hand, and so all these these scopes and the meters actually generate some values, and we use these values to model, prepare or create a model actually, which can tell about what is the gesture exactly. Now the second so that is also getting exercised in the research domain, but again it's a bit costlier part. Now talking about the second approach is the computer vision approach, where we actually take snaps or take video footages or the real-time video streams, and certainly we process that to analyze those videos for these gestures. So there has been a good work being done in that area. So gestures can be recognized through pre-curated features like shape, orientation, appearance, direction of motion, and typical encoded features in the dimension of image processing could be means optical flow, image gradients, and divergence field kind of the things. And certainly all these features created, primary features and secondary features created, can then be given for some kind of a statistical model like HMM, hidden Markov model, or something like that, or some machine learning approaches can then be used. There are the typical other approaches also, like principal component analysis, PCA. So a good work has been done in that area. So many researchers has actually used these kind of approaches to do that for different sign languages, let it be for American, for Vietnamese, or any XYZ exactly. So this is what the thing. Then we had as well seen more improvements in training the models, utilizing more advanced modeling techniques like neural network and the deep neural network exactly. So with the advancement and what you say, the machine learning and the deep learning approaches, and the underlying hardware resource or the computational resource requirement for I mean, training these models, uh, we are improving a lot exactly. And this is this paper itself actually talk about one of such improvement actually in that dimension. So this is what the proposal we had given is. So it's just a typical framework. So what we had actually used is the 3D CNN for it. And why we had used it, I will talk in the next slide exactly. And so what we do here is we simply take a video sample. It could be an offline video sample. It could be a log exactly. It could be a video stream for real-time application as well. So what we do is we have to have some small clips exactly being segregated out. And then so that video clip is actually is nothing but images of the frames in a timeline. So then what we do, we have to actually extract out the frames, image frames, and we have image sequence like that for a particular gesture kind of the activity. And that image sequence is pre-processed. Actually, the pre-processing has to be done for some reasons. So, and pre-processing is much more required when you are working out with the real-time video footages exactly. So we have the problems of background noise. We have the problem of image quality. We have the problem of different kind of the noises and all. So then after pre-processing, then we get more improved image sequence. And then what we have to do is we have to create a 3D CNN exactly. Now creating 3D CNN is the main thing. So no way baseline architecture is already available of it. So it is something like this, and how it different is different from typical 2D CNN. There are the limitations of the 2D CNN exactly. Actually, what happens in case of the 2D CNN, it only takes a 2D input, and the important thing is the filters or the convolution filters exactly are of the 2D size. And what happens is, so they actually operates on separate frames. Whereas when we talk about the gesture, it's in a time domain. Dynamic gesture is in a time domain, and certainly every second means consecutive frames have some relation. So in order to get a gesture in a time domain, we have to even look about the relation between or connectedness between two consecutive frames. So that is what the important thing we had actually seen and exploited here. So we use 3D CNN. So the difference is here the convolutional filter is a three-dimensional filter exactly. And then the important thing here is to work out on the hyperparameters exactly which are important here. So the typical filter typical size filter size rather I should say. And so so that we can get up appropriate feature maps in every layer of the convolution operation. So this is what it happens here in case of convolution neural network. So there are the layered convolution operation, the max pooling operations. So pooling, rather say I should say pooling operation. Pooling operation is done to means reduce the dimension of feature map exactly, dimensionality reduction exactly. So that this is done to actually reduce the size of the feature map in order to reduce the computational complexity, and so that we can have all that processing done in more real time. So that's the thing is done. So the dense layer is at the last side where we actually do the classification part, or I mean that's the exactly classification side of this convolutional neural network. Dropout and regularization are the additional things which are done here. Dropout. So these are the strategies exactly. Dropout is actually we have what we do in case of the dropout is we drop some of the neurons. So what happens is many times we are not actually getting more good accuracy. So it's sometimes our model is actually maybe is trying to cram the things, or so memorize the thing. So what we try to do is we do some drop some of the neurons and some of the filters. That's the thing. And softmax is the last layer that actually does from the probability of the classification or the class for a particular input. It actually gives us the 0 1 values for a more highest probability, means the highest probability class will get the label exactly as this. So this is the proposed model, which where we actually had taken three convolutional layers and the three max pooling layers. Next to that is the flattening layer, that is, and then so what is to be done after means in case of the flattening, exactly what happens in the next part of the classifier. What we have to take the linear or a vector of the inputs. So before that we actually have a voluminous kind of the feature, so that is to be flattened in a single dimension vector, and then it is given to fully connected network, a classification network of the neurons. So that's the dense layer exactly. And then these dropouts are done to more optimize the model exactly. So that's the thing. Talking about our experiment, so this is what the thing we had done. So the gesture data set, sign gesture data set, actually we had considered 20 gestures, something like ache, admire, adult, answer, ask. So so these are the signs where means the maybe situation you can say, or which are actually explained through some science exactly in any language of any nation exactly, we can say. So so we generally don't means explain these kind of situation by some word. Rather, we do some gestures corresponding to that, and the signs are given for that. So answer, calm, close, compare, complain, like that. So we actually had synthesized 120 video for samples for every of these gestures, and in all 2400 video clips. And then we, in order to have a training, so what we do a five-fold cross validation, and that is what we divide it into 80-20 ratio for training testing. So that's the thing. So these are the typical images for the video clips, means synthesized exactly corresponding to every of those gestures. So these are for 3, 8. So first one is for 8. Then second one is for near. What was the sign for explaining that I'm near to you or you are near to me? Third one is to admire. So just with a sign, we can actually communicate many things to any second person. So in order to have some an intelligent machine created, or in order to have some human machine interaction, we have to actually do this kind of the modeling. So then the performance measures, these are the typical performance, standard performance measures which are used for it after experimentation. So experiment was done on a machine 4th generation i7 core i7 machine exactly, is with a 16 GB RAM, and with a GPU exactly of GTX 1050 type, 4 GB GPU. And this was done exactly. So 100 epochs for one training exactly, and five-fold cross validation exactly was done. So what we achieved was a 99% training accuracy, or almost 100% training accuracy, and 88% validation accuracy. So this is important. So from the graph itself, we can very well see it. So why 100 epochs only? So we can find it that uh, from 60 epochs itself, we had got somewhat constant kind of accuracy, and we feel that that validation accuracy will not be further increasing. Then we can stop it here. So that's the idea exactly. So for every class, this is the table actually showing the precision recall values for it. So we can say in many cases, we got a TPR, or the true positive value, or the recall value as 1, means 100% correctly classified. So while the precision also in some cases is 100%. So and a good support exactly also we get in this case. So on an average, what we get is means 88% or nearly 89% of the true positive rate, and so is the accuracy is somewhat about 88%. So 88.24 is the final accuracy in case of our model exactly. So if when we tried it to compare with other models, so this is what we got it good exactly. So if I talk about other contributions from in the literature, so I find this 81%. This is from a journal paper of 2016, EuroSIP journal. This one is 86% is from CVPR paper, is a top rated conference paper of 2019. And this last one is from very recent 2020 conference. It's a top rated conference of the area of gesture recognition. So when I compare with these, so we get a good, not, it's a slighter improvement, but even means it is good enough exactly. So that's the thing. So this here we conclude is means our objective is achieved. Objective is achieved by using 3D CNN for gesture modeling, which itself provide a exceptionally good accuracy, and proposed method can then be used to reduce the communication gap between different means category of the pupils exactly. More importantly, the disabled pupils. Different combination of static and the gesture hand means static and dynamic hand gestures can be means modeling for these can be done for Indian Sign Language translation exactly. These are some means references being used for this proposed task, and here we thank you. So this is all. Means any question if anyone have, please.
Thank you very much. Do we have any questions? Or anyone is able to give a question? Thank you, Abdelrahman. Thank you very much. Let us go to the last one.
Yes, sir. Am I audible, sir?
Yes. So I think you share the video.
Yes, sir.
Would you like me to play the video or?
Sir, actually, I was having network issues as well as, sir, my laptop is not working properly, so I have done this. So can I now proceed, sir?
Now you can share you can start your presentation.
Yes, sir. Yes, thank you, sir.
Thank you very much.
Sir, is my screen visible?
يعني you are please share the okay, that's not. Okay, go ahead.
Sir, okay, thank you, sir. A very good afternoon to all our respected and honorable members present out here. I hope you all are well and good, staying safe in these tough times. So my name is Arjun Gogoi, and I'm currently pursuing Bachelor of Technology in Computer Science and Engineering at Dibrugarh University, India. And I am going to deliver a presentation on our research work entitled as Assamese word sense disambiguation using Cuckoo search algorithm. My co-authors are Dr. Nomi and Mr. Loikho Jyoti Nath. So these are the outlines of my today's presentation. A brief introduction to word sense disambiguation, related works on word sense disambiguation, motivation, proposed methodology, and followed by various pre-processing techniques, then proposed work, and lastly conclusion and various references that we have used. So what is word sense disambiguation? Word sense disambiguation is a problem of determining which sense of a word is occurring in a particular context or sentence. So there can be various ambiguous words might be present in our sentences. But as a human, we can identify what the ambiguous word means to a particular context, but how a machine will know. So our objective is to identify such ambiguous words and to find its actual meaning using various methodologies. So let us take an example. So the first example is মানুহৰ জীৱনত সদায় এটা নিৰ্দিষ্ট লক্ষ্য থাকিব লাগে. So this is in Assamese language. And the English translation is every person must have an aim in life. And the second example is লক্ষ্য মোৰ ভাল বন্ধু. The English translation is লক্ষ্য is my good friend. So the first example, first sense denotes aim and the second sense denotes a name. So there is clearly an ambiguity problem. Challenges. So there are various challenges in word sense disambiguation, and especially in Assamese language, such as differences between dictionaries. The major problem of word sense disambiguation is to decide the sense of the word because different senses can be very closely related. Secondly, interjust variance. Another problem of word sense disambiguation is that it's generally tested by having their results on a task compared against the tasks of human beings. Word sense discreteness. So here words cannot be divided into discrete sub-meanings. And lastly, difference algorithm for defined applications. So for example, in machine translation, it takes the form of target word selection, and in information retrieval, a sense inventory is not required. So apart from all this, there is lack of Unicode, lack of NLP tools, for example, Lematizer, a complete text corpus, and all that. So the types of WSD. First one, knowledge-based approaches. So it basically relies on knowledge resources like WordNet, Thesaurus, etc. It may use grammar rules for disambiguation or may use hand-coded rules for disambiguation. So for example, word co-occurrences and Lex algorithm. Secondly, supervised learning. So it is the learning of the model where we have the input variable and an output variable, and we use an algorithm to learn the mapping function from the input to the output. So for example, naive Bayes, decision tree, and many more. And lastly, unsupervised learning. So it is a learning where the input data is present and no corresponding output variable is there. So for example, various clustering techniques. So these are some of the related works that we have considered for the proposed approach. So as you can see here in the slide, for the language Marathi, the language family is Indo-European, Indo-Iranian, and all that. The approaches used were unsupervised graph-based word sense disambiguation method. The title of the paper is Marathi word sense disambiguation using genetic algorithm. And these are a few comments that we have shown here in the slide. So motivation. So our motivation is just quite straightforward, as WSD allows the users to make ample use of available technologies such as machine translation, etc. So therefore, we have made an attempt to disambiguate the Assamese ambiguous words using unsupervised word sense disambiguation. Proposed methodology. So the proposed work is an unsupervised methodology. So we have proposed an unsupervised methodology that is Cuckoo search algorithm to fulfill our objective. So what is Cuckoo search algorithm? So in various operations research, Cuckoo search is an optimization algorithm developed by Singh Young and Suas Dev in 2009. So it was basically inspired by the obligate boot patriotism of some cuckoo species by laying their eggs in the nest of other host birds. So for example, if a host bird discovers the eggs are not their own, it will either throw these alien eggs away or simply abandon its nest or build a new nest elsewhere. So first we extract all the possibles for the Assamese word net. Then we apply various pre-processing techniques such as tokenization, stopwatch removal, and lastly stemming. So in the tokenization part, so if tokenization is basically breaks the raw text into words, sentences called tokens. So these tokens help in understanding the context or developing the model for the word. So for example, Loikhamur Valbondu. So this example I have shown you in the previous slide. So after tokenization, it becomes Loikhomur Bhal Bondhu. So it basically breaks into parts. And stopwatch removal. So in this section, various stopwatches are removed. They can safely ignored without sacrificing the meaning of the sentence. According to the references that we have used, a total of 125 words have been found. So for example, Tatmur Bahire Kunu Nasil. So the English translation is there was nobody except me. Here the word Bahire will be removed after applying stopwatch. And lastly, stemming. So stemming could be defined as a process that strip of a set of suffixes from the word to get the base word. So which part to strip? So for example, for a word args, the root word of args is args. The word ed is a valid suffix here, and it will be popped off in this section. So this is the implementation of the pre-processing phase that we have done in a proposed approach. So this is a pictorial diagram of the proposed approach. So first we take the input, then we pre-process the data, as I have already mentioned in the previous slide. Then we using the input sentences, we have to identify the ambiguous word. So to do it, we extract all the possible senses from the word net. So if it has more than one sense, then it can be said as an ambiguous word. After that, we can generate a population of n cuckoos. So these cuckoos are the extraction senses that I've already mentioned. So among all the population, we have to take two cuckoos at a time. So one is I or the other is Z, as we can say, and to calculate similarity measure. So for the similarity purpose, we will be using cosine similarity, which I will show in the next slide. And then if the cuckoo score of the one cuckoo is greater than the Z cuckoo, then we will simply replace the Z cuckoo by I, and we will finally sort the cuckoos by their score and return the score, return the cuckoo with the base score. So the base cuckoo will be the correct sense or the required sense that we want. So the cosine similarity. So cosine similarity measures the similarity between two vectors of an inner product space. So it basically measured by the cosine angle between two vectors and delivers whether two vectors are pointing in the same direction or not. The basic idea is if the cosine angle is smaller, the higher will be similarity value. It is mostly measured to measure the similarities in text analysis. So this is the formula that we have used in the proposed approach where A and B are two vectors. So data set. So for the experiment, we evaluated a global algorithm developed and applied a sense annotated Assamese corpus. The sense inventory used in this research has been derived from the Assamese wordnet. There are a total of 50,000 words, and among them, 15,606 words are ambiguous or as given in the references. Experiment and results. So these are the formulas that we have used for the experimental purpose of the proposed approach, and these are the results. We have got precision is about 87.5 and recall about 84. So comparisons. The proposed approach results on compared to the available works on Assamese WSD. So let me tell you a point here. So this is a work that we have done earlier, and we have chosen this work to compare with a proposed work because there is no such unsupervised research work done in Assamese WSD till date. And our proposed work affirms our previously done work. Conclusion. So in this paper, we have made an attempt to disambiguate the ambiguous word using a global algorithm, which can be highlighted as a significant contribution to the natural language processing. So we have got precision about 87.5%, recall about 84%, and F1 score is about 85.71%. So in future, the scalability of the proposed system can be improved by adding more ambiguous words to the Assamese language. So these are all the references that we have considered for the proposed approach. And with all this, I want to conclude my presentation. Thank you, sir.
Thank you very much. So any questions regarding the word synthesis abbreviation within the next algorithm? Any question? So my question to you is how to generalize this such that other language can be can use your approach.
Pardon, sir.
How can we generalize this such that other languages can benefit from your approach?
So basically, Assamese is a very low resource language, sir. It doesn't have a Unicode as well, sir. So it doesn't have NLP tools such as Lematizer, Stammer, and all that, sir.
Low resource language.
Yes, sir.
I am not familiar with the language, so.
Yes, sir. So it is basically an Indian language, sir. Our 16 million people is speaking this language, sir.
So any other question? We reach the end of today's session.
Sir, can I say something, sir?
Yes.
Sir, sorry for the inconvenience.
Yes,
sir.
please. Yes.
So sorry for the inconvenience caused, sir. Sir, actually, I was having technical issues with my laptop, sir.
No.
That's why.
You know, in connections, we always have.
Thank you, sir. Thank you, sir, for understanding, sir. Thank you very much, sir.
We reach the end of today's sessions. Tomorrow we will start, and everything is on the website. And today we still have the big event. Dr. Mona Diab, Professor Mona Diab is going to present to us give us keynote speech, and it is at 5 GMT, which is 9 p.m. UAE time and 7 p.m. Cairo time. And please look at your time in your region. And the talk is about faithfulness in natural language generation in an era of heightened ethical AI awareness, opportunities for machine translation. Everyone is invited, and usually she's one of the speakers who I advise you and everyone in the NLP field to attend, because she has a very good experience and she is a very good speaker. Thank you. And before I leave, I would like to say hello to Professor Ali Ferghali, because from long time I didn't see him or talk with him. and it's an honor to have you with us today.
Thank you very much. Thank you.
Thank you, Professor. He is my godfather, Professor Ali.
Thanks.
I learned a lot from you.
Thanks.
Thank you, everyone. And we reach the end. And don't forget the keynote speak. Assalamu alaikum.